All right, so I think we can get started. Just want to remind you guys, homework, exam one is Monday. Okay, so for you guys taking labs on Friday, you'll meet in region 14, and then if you are having lab on Wednesday, we'll meet in faculty 108. Okay. Um, I also just wanted to put up the homework number for due date here. So it's going to be, I think, on the 16th. Tuesday. Okay. So I will probably put it up on Monday after the exam at some point, and then you guys can start working on that. And it will be on Tuesday, the week after next week. Okay. All right. Um, Also for lectures next week on Wednesday and Friday, because you guys will be in seat on Monday already. So then for those two lectures, we'll meet online. Okay. Then the normal patterns for the meetings will resume the week after that. All right. So today's in-seat classroom in disinfection that's assigned to Jaden and Alyssa. Okay. All right. So last time we took a look at charges. So basically two types of charges, positive charge and negative charge. Like charge will repel each other, and then opposite charge will attract each other. Okay. Um, Charge is not continuously, so it's rather quantified. So that means there's a charge will have an increment of with this quantified number 1.60 times 10 to the negative 19, which is the charge of a proton or an electron that will have. Electron will carry negative charge, proton will carry positive charge. Okay. We also talk about like conductors and insulators. What are the difference? Um, what's the main difference there? So it's just one has conduction electron that can move freely. That is for a conductor, and then for insulator, it doesn't have a conduction electron or at all that can be moved from atom to atom. You can charge a particle by contact, so then bring charges to the particle. So then charge will be transport to that particle. Or you can do charge by induction. That means bring a charged particle close to, say, a system or part of conductors. Then after that, you can separate the conductors, and each will carry charges. Okay, opposite charges in that way. We also talk about how strong is the interaction between charges, which is governed by Coulomb's law. So interaction force of any two charges is equal to K, Q1, Q2 absolute values divided by separation square. Okay, Q1, Q2 are the charges of the two, and K is the Coulomb's constant of 8.99 times 10 to 9 newtons times meters square over c square. Sometimes you see people just write 9.0 as K, so that's fine too. Okay, it's just you just round it up because then the difference is only like roughly about 1/1000. Okay, so that doesn't make any significant difference there. Okay, so if you use 9.00 times 10 to the 9 for K, that should be fine too. Okay, all right. The direction of the Coulomb's force or the electrostatic force is along the line connecting the two charges. And then depending on if you are having like charges or opposite charges, you will have repulsive force or attractive force. Okay. So here's a figure showing you different scenarios. Okay. So repulsive forces for like charges, and then attractive forces for opposite charges. Okay. Um, just keep in mind that charges or forces on the two charges, they are in a pair of action and reaction forces, okay? Because they are having the same magnitude but pointing in the exactly opposite directions. If you have multiple charges in space, then the force on a particular charge should be the force on this charge from all other forces, all other charges, okay? So force on Q Q1 should be coming from force by Q2 on Q1, Q3 on Q1, and Q4 on Q1, okay? And then when you add those three forces up, you are doing vector addition, okay? So that means you are going to do either component method or triangle method, okay? So today we are going to check on the new sections here. Now, for force between two charges, it looks a lot like force between two objects, okay? The gravitational force between two objects, okay? So in that sense, then the gravity there plays a role here. So when we learn gravity, we know that if you are near a large object, for example, the Earth here, then the force is equal to mass times gravity, okay? The gravitational field of the Earth, okay? So F equal to mg. Similarly, we can write the same thing here for a force object. Okay, so on the charges, so if you have two charges here, if you have one charge here, if you have another charge that's nearby, so then this charge here on the right, we'll call it as test charge. Okay, Q naught will experience a force by this charge. And it's by Coulomb's law here, F equal to K, Q, absolute value, and Q naught over R square. So we can define a similar field over here in the previous case when you talk about gravitational force, we say there's a gravitational field. In this case, you can say there's an electric field, okay, because you have charges here. So then force, you can rewritten it as Q0 times E, just similar as force equal to mg, okay, where G is the gravitational field, E here is the electric field, okay, F equal to Q naught times E, all right. In that case, E is equal to K, absolute value of Q over R square, okay. In the gravitational field, a G is equal to capital G times M divided by R square, okay. So it's in the previous slides over here, all right? So that's where G is from. So pretty much a simple, similar expression here, but just because the difference is you have different constant. In gravitational field, you have gravitational constant G, you have mass. In this case, in electric field, you have Coulomb's constant, you have charge, okay, and then divide by separation square. All right, so these two types of fields, they are similar in many ways, okay? All right, so according to the definition, F equal to Q times E, then E is equal to F divided by Q0, okay? Now, force is a vector, so you should write this in vector form. Electric field, then it's also a vector, okay? So E is also a vector form due to that, because force is a vector, Q naught is a scalar quantity, okay? The SI unit for electric field is newtons over coulombs. Newtons comes from force, coulombs come from the charge, okay? All right. And here Q0 is the test charge, okay? It serves to allow the electric field to be measured, but it's not large enough. So typically, a test charge you are using is a small charge. Just like when you are on the surface of Earth, if you want to know what's the gravity here, you will measure the weight of the object and then measure the mass of it, and then use the weight divided by the mass to get the gravitational field or the gravity G. Okay, so in that scenario, the mass you are using is small compared to the mass of the Earth. Okay, similarly, for an electric field, the test charge should be small enough compared to the charge, okay, and that produce the electric field. Okay. All right. So if we know the electric field, then we can calculate the force on any charge. Okay, so if there's an electric field around, if you put a charge inside, then force is equal to Q times E. All right, so in this fashion, you can just rewrite the equation from the previous slide here. Now, depends on if you have a positive charge or negative charge. Okay, so this is the difference between electric field and gravitational field. So in electric field, the force produced depends on the sign of charge. While in gravitational field, because mass is always positive, so you don't get negative sign there for the force. Okay. All right. So if you have a positive charge, then electric field and electric force are in the same direction. On the other hand, if you have negative charge, so electric field and electric force, they are in opposite direction because of the negative sign. Okay. The electric field by a point charge. Okay, so you can imagine if this is a point charge, it will produce an electric field, E field. Okay, it's going to be pointing away from the charge. Okay, because you can put a test charge here, a positive test charge here, to see the force direction of the force should be in this direction. That means the electric field should be in this direction. Okay, so if you have a positive charge, it will produce electric field radially away from the charge. All right. Now, on the other hand, if you have a negative charge, then the electric field produced by this negative charge will be pointing towards it. Okay. So if you put a test charge somewhere here, you'll see that the force will be attractive force. So that means pointing towards the negative charge. Okay. All right. On the other hand, if you see an electric field like in this fashion, then you know this guy will be a positive charge. And if electric field are pointing towards a point, then that means the charge will be negative charge. Okay. The magnitude of electric field due to a point charge will be equal to this guy, because electric field is equal to electric force divided by Q0. And electric force for a test charge Q0 is KQ times Q0, absolute values divided by R squared. So you can see the Q and Q0 and Q0 will cancel out. Okay, so then that equals to K Q over R squared. Okay, so this is a 4-point charge. Okay. This should also apply for a spherical charge distribution for the electric field outside of spherical charge distribution. Okay, due to the symmetric. For the direction of it, okay, if it's a positive charge, then it's pointing away from it. Okay, so you can see in that case, so then direction can be indicated by this, if you remember, this is a unit vector, just indicate the direction of it. Okay, so from the source to the point of interest. Okay, this is the source, this is the point of interest, so then it's pointing away from there. Okay, if you have multiple point sources, then electric field should be, so for example, if you have other points here, there, electric field over there should be equal to summation of the electric field produced by each of the point charges. Okay, so then just again, electric field, this is similar to electric force. It's a vector. So when you are doing the summation, you want to do vector addition. Okay. All right, let's take a look on one example here. So this one says 2-point charges lie on the x-axis. A charge of positive 2.40 picocoulomb. Okay, P stands for 10 to the negative 12. Okay, is at the origin, and a charge of minus 4.80 PC picocoulomb. Again, it's at x equal to minus 10 centimeter. It's asking you what third charge should be placed at x equal to 220, so that the total electric field at x equal to 10 is 0. Should be 10 centimeter here. So let me draw a figure here to represent the problem here to get you guys started. All right, so this is what the problem says. It says on the x-axis, if this is the origin, x equal to 0, there's a charge of 2.4. So that's this guy here, Q1 equal to positive 2.40 PC. And then it says at x equal to minus 10, let's say somewhere here, this is minus 10. There's a Q2, a second charge, minus 4.8 PC. It wants that the electric field at x equal to 10. So E at this point to be 0. It's asking you, where should you place a third charge, Q3? So let me say X3. I think it's asking, oh, X3 is equal to 20, okay? So it says X3 to be at here, or Q3 to be here, where this is 20. Q3 is sitting there. All right. So this is your point of interest, P. You have 3 point charges at x equal to minus 10, x equal to 0, x equal to 20. And you want this to be at point P, this E equals to 0, okay? So that's the problem here. I'm going to give you guys a couple minutes to maybe think about how you want to solve this, and then we can take a look at this together, okay? After that. All right. So we can see at this point, okay, there will be a E field by Q1. Now Q1 is positive, so then E field by Q1 on this at this point P will be in this direction, right? E1 in that direction. By E2 minus, so if this is a minus, then electric field should be pointing towards the minus charge, right? Electric field is pointing away from positive charge towards the negative charge. So then by E2, it's going to be in this direction. All right. Now for E3, we don't know if it's going to be a positive charge or negative charge, right? So, but it says that total E field is going to be 0, right? So then total E, that should be equal to E1, the electric field by Q1, plus the electric field by Q2, plus the electric field by Q3. And that's equal to 0, okay? So you can see then for E3, the direction of E3 should be depending on the sum of E1 and E2, right? So if E1 is greater than E2, then E1 plus E2 is pointing in that direction. So then E3, oh, let's do it this way. So if E1 plus E2 is in this direction, then E3 has to be in that direction, right? The other way around, so if E1 and E2, E1 plus E2 is in this direction, then E3 will be in that direction, okay? So that total field should be equal to 0, okay? So like two scenarios here. So what we really need to do is like do E1 plus E2 first, okay? We can do that because we know Q1, Q2. Now E field for point charge is equal to KQ over R square, right? Absolute values. And then we can determine the direction by, we already determined the direction. So for E1, it's going to be in that direction. For E2, it's going to be in that direction, okay? All right. Now R1 is going to be this distance. This will be R2, okay? Then this will be R3, all right? So E1 is equal to K Q1 over R1 square. E2 will be equal to K Q2 over R2 square. Okay, you should take absolute value here for just the magnitude. Okay, so let's just focus on the magnitude here first. And we know if you want to include directions, we know that E2 will be negative, right? Because it's pointing towards the left. If we take to the right to be positive, E1 should be positive, okay? So E1 plus E2 then will be equal to positive of K Q1. We can take in the numbers here. You can do K here, or you can leave it out for right now, but we can do this. Q1 is 2.4, okay, PC, picocoulombs, divided by R1 is 10 centimeter squared, okay. Let me put it this way, plus or minus K, because for E2 it's in the negative direction, times absolute value of Q2 should be 4.80, okay. PC divided by R2 will be 20, right? It's 10 here plus 10 there, so 20. Okay. So you can kind of see here, this is 2.4, right? This guy is 2.4 times 2. So 2.4 times 2 here. This guy will be, so 20 square will be equal to 10 square times 4, right? So we can see that because this is K 2.4 over 10 square, and then multiply by 2 over 4, which means 1/2, right? 2 over 4 is 1/2. So this is 1/2 of that guy, right? So this is K 2.4 PC over 10 centimeter square minus K, you can do 2.4 PC, okay, divided by 10 square, and then multiply by 1/2. 1/2 comes from 2 over 4, okay? So then this would be just 1/2 of K 2.4 PC over 10 centimeter square, okay? So this guy will be positive. Now K is a positive number. It's the 8.99 times 10 to the 9 or 9 times 10 to the 9, okay? So it will be positive. All right. So E1 plus E2 is positive. That means we are having this scenario over here. E1 plus E2 is pointing towards the right. Okay. So then E3 has 2 points in this direction. Okay. So this is what you would have for E3. So that tells you E3. So by E3 is going to be in this direction. That tells you E3 is going to be, because electric field by E3 is pointing away from it. So then E3 will be positive charge, okay? So we can determine the sign for Q3. Q3 will be a positive charge, okay? So this says E3 will be negative, okay? In the negative direction or in that sense. Then Q3 will be positive, okay? All right, now we can try to see if we can solve for Q3, okay? Now for E3 is equal to, if we start from here, so E3 then will be equal to minus E1 plus E2, right? So then that means equal to minus 1/2 K 2.40 PC over 10 centimeters square, okay? You can just keep this expression for right now. And E3, it should be equal, for the magnitude of it should be equal to K Q3, right? Over R3 square, which is K Q3. R3 will be, sorry, that wasn't in the window there. For R3, so E3 is equal to K Q3 over R3 square, right? For the magnitude. And R3 will be equal to 10, right? Because this is 20, this is 10 here. So that's R3. That will be 10 centimeters square, okay? So then the magnitude, for magnitude wise, this guy should equal to this guy, right? The sign here is the direction. For the magnitude, you just focus on the positive term here, okay? So you can set the two equal to each other. You can set up like 1/2 K 2.4 PC over 10 centimeters square. That should equal to K Q3 over 10 centimeters square, okay? Now you can see why I didn't plug in K in the first place, right? Because K and K here will cancel out. Now there wouldn't be a problem if you did put the K of 8.99 times 10 to the 9 there, okay? Just you have to keep track of the numbers there. But here KK cancel out, this 10 centimeters square and 10 centimeters square will cancel out. So then it will tell you Q3 is equal to 1/2 of 2.4 PC, right? So Q3 then will be 1.2 PC, all right? Positive, okay? So this one is a little bit complicated. It's one-dimensional low, so you can use either positive or negative to indicate the directions for the field, okay? All right, so you're starting with, at your point of interest, the electric field is going to be equal to the summation of the electric field by the three charges, and then that's equal to 0. That's the problem once. Now, E1 and E2, you can calculate them. You can add them up and then see what's the number you get, okay? As I say, you can plug in K here as you want, if you want, but K is that number, okay? It's a constant number there, but you don't have 2 here. So once you figure that out, E1 plus E3, E2, you figure that it's a plus, okay? It's greater than 0, that means it's pointing towards the right. So that means E3 has to point towards the left, which will tell you what's the sign for the Q3. It will be positive, because for positive charge, the electric field points away from it, okay? So then E3 is equal to minus of E1 plus E2, okay? So then it means minus of that guy. Also, E3 can be given by the electric field for point charge KQ3 over R3 square, and then you can set the two equal to each other to solve for your Q3. Okay, so that's your whole solution there. All right. Questions you guys might have on this one? All right. So if not, then we will take a look on a second problem here. Now this one says an electron has an initial velocity of 2.00 times 10 to the 6 meters per second in the positive x direction. Okay, so in the x direction here, it enters a region that has a uniform electric field, okay, in the positive y direction. So in this case, positive y is in the downward direction, okay. E field is given as 300 newtons per coulomb. It's asking you to find the oscillation of the electron. And then how long does it take for the electron to travel 10 centimeter in the x direction, and through what angle and in what direction is the electron deflected while traveling 10 centimeter in the x direction? Okay, there's a hint given here. So force should be the force that electron experience in this case should be the electric force. Okay, so electric force is equal to the charge times the electric field. So E is given. Now Q for electron. So a lot of times a problem like this will not tell you the charge of an electron because it's a constant fundamental number. Okay, so it should be something you can look it up. For the electron, it's 1.6 times 10 to the negative 19 coulombs. All right. So if you can figure out the force, then you can calculate the oscillation. Also, the mass of the electron is not given. So yeah, there are two pieces of information not directly given, but those are fundamental numbers you can look up. But I'm going to just put it out here. Okay, so for electron, charge of electron, typically it's written as E. Okay, so just keep in mind E is the Q here. Okay, that's 1.60 times 10 to the negative 19 coulombs. The mass of an electron is 9.11 times 10 to the negative 31 in kilogram. So this one is similar to like a projectile motion, right? You have a initial velocity, and then now you are having an electric field instead of gravitational field, but similar fashion, right? So in that case, the only thing here is because electric field is pointing downward. Sorry, I keep forgetting to pull this screen over here. Q is equal to, for the electron, charge is equal to electron charge. Okay, E stands for electron charge. It's 1.6 times 10 to the negative 19. Mass of electron is 9.11 times 10 to the negative 31. Okay, the E field is in this direction. The electron is now entering this field. Okay, so for the force here, because it's an electron, it's a negative force, negative charge. Okay, so the electric force should be in the upward direction, right? It's in the opposite direction of the E field. So you'll see if it start with this guy here, V0, it's going to probably going in that way, right? Due to this electric field or electric force. You probably need some more equations here because it's a projectile motion similar to a projectile motion over here. So, let's say this is two-dimensional motion, okay? So then for two-dimensional motion, x equal to x0 plus v x times t, vx equal to v0x plus ax times t. All right. The third equation, I don't think you need it here, but the third equation will be vx squared equal to v0x squared plus 2ax times delta x. Okay. In the y direction, y equal to y0 plus v y times t. Or actually, plus 1/2 ax t squared plus 1/2 ayt squared. Okay. Similarly, vy will be equal to v0y plus ayt, and then vy squared will be equal to v0y squared plus 2ay y minus y0. Okay, or delta y. All right, I think let's take a look at this one together because there's so many equations that you might have to pick. All right, so we might not have enough time for you guys to solve this in the class, but we can take a look at the solution together. Okay. So A is asking what's the acceleration for the electron. Okay, so you can see when it enters this field over here, so then there will be electric force, okay, which is because this is charge is negative. For electron, it's a negative charge. Electric force is in the opposite direction of the electric field. Okay, so in that case, so that's the only force on the electron, and then that should give you the acceleration for the electron. Okay, so this is in the y direction. It tells us this is x direction, pointing downwards is the positive. Okay, so this case, the force you have on the electron should be equal to E times the electric field. Okay, so for E, I forgot to put a minus sign, but for electron it's negative. Okay, negative 1.6. So negative 1.6 times 10 to the negative 19 C times the electric field of 300 newtons over Coulomb. It says that's in the positive y direction. So let me use y with a hat to denote the direction of positive y. Okay, so this means positive y direction. So the fact that you have negative sign here, that means force is in the negative y direction. Okay. So you can calculate this. How much force is that? I didn't calculate. I actually calculate A right away. So then acceleration of it should be equal to the force divided by the mass of it. Okay, so I did the force. I use this 1.6 minus 1.6 times 10 to the minus 19 times 300 newtons over Coulomb times y positive direction divided by 9.11 times 10 to the negative 31 kilogram. Okay. So I got for the acceleration, this is minus 5.269 times 10 to the 13 meters per second square. Okay. In the y direction. So that's my acceleration. Okay. It's asking you for acceleration. That means you want to specify the magnitude and the direction as well. So in this expression, okay, this is the magnitude. The negative y is the direction, okay, negative y direction. So you have that already there. So you can see your acceleration is only in the y direction. So that means ax will be 0. Okay, so this term is 0 actually. This term is 0. Okay, and then that term is 0 too. Okay, so ax is 0. You don't have to worry about ax. Okay. B is asking you how long does it take for the electron to travel 10 centimeter in the x direction. Okay, so this is a two-dimensional problem. So it will, so for 10 centimeters, say somewhere here, let's say from here to here is that 10 centimeter. Okay, this is your x naught, this is your x. So x minus x naught is equal to 10. X minus x naught is equal to 10 centimeter. All right, so that's your change in x. Basically, it's asking you for time t. All right, so it tells us that when it enters the field, it has a initial velocity of 2.00 times 10 to the 6. So that's your initial velocity, right? In the x direction only, because it's horizontal only. So it's that 2.00 times 10 to the 6 meters per second. All right. So then it's asking you what's the time t here. You are having the change in position in x direction, so you'll be looking at this equation or that equation probably, but you probably will figure out in this equation you have x and x not there, and then you're looking for t. Basically, this should be v0x, initial x direction velocity times t. So this will be the equation you use to solve for t. Okay. So x equal to x naught plus v0x times t. You are solving for t. You move this guy to the left side. Okay, so all right, here you go. X equal to x naught plus v0x times t. You're solving for t. So move x naught to the left hand side. X minus x naught equal to v0x times t. So then for t is equal to x minus x naught divided by v0x. Okay. X minus x naught is 10. So 10 centimeter divided by v0x 2.00 times 10 to the 6 meters per second. Okay, it's centimeter on the top. That means you want to do conversion to meters times 10 to the minus 2 meters. Okay, that will be your t. So your t will be equal to 5 times 10 to the minus 8 second. Okay. Minus 8 here. All right. For part C is asking you through what angle and in what direction is the electron deflected while traveling that 10 centimeter in the x direction. Okay, so you can see if it goes 10 centimeter here, it probably goes up in that way, right? So this is just the x component of the its trajectory. So then it's probably now going in this direction. All right. So then we are looking for what angle is this? See if you can see that clearly. So when it's at 10 centimeter, probably means somewhere there for the trajectory of that, right? Because it's having a sort of like projectile motion. So then it goes in that direction. We are looking for this angle. Okay, so for this angle, you have to know what's the velocity, x component and y component, right? This is the velocity in that direction. So velocity goes in that direction. You need to know the y component and then its x component, okay, in order to figure out the angle. Because the angle, if you remember, should be equal to tangent of Vy over Vx, okay? So this is some knowledge back in the last semester when we talk about vectors, okay? So velocity is a vector. You want to know what angle now it's moving at. So then you want to figure out its x component and y component. And then for the angle, it's tangent inverse of Vy over Vx, okay? Now for velocity x direction, um, it will be constant because in x direction there's no oscillation. Okay, so this will be equal to the original 2 times 10 to the 6 meters per second. Okay, for velocity in y direction, we have to figure out it this way from here. Initial y should be 0 because initial velocity only has the horizontal component. Okay, so this guy was 0. Now you just need to do ay times t. Okay, the oscillation of the electron is purely in y direction. So your ay should be equal to this guy. Okay, that's your ay. All right. Now t, you have t in part B, okay, over here. So you can solve your Vy. All right. So for 3, you want to solve for Vy first. Vy is equal to V0y plus ayt. Okay. Initial, that's 0 for the velocity plus ayt. So that equals to minus 5.269 times 10 to the 13, what we got from part A, meters per second squared, times the t we got from here, 5.00 times 10 to the minus 8 second, right? So then you get minus 2.63 times 10 to the 6 meters per second, okay? That's your V in the y direction. Now the directional angle you can calculate tangent inverse of Vy over Vx, okay? So you would have tangent inverse of minus 2.63 times 10 to the 6 meters per second over Vx 2.00 times 10 to the 6 meters per second, okay? That will give you minus 52.7 degrees. All right, so that means because this is your x and y coordinates, right? So that means in this sense, minus means above x. So this will be your direction. Positive x and y, this is the minus 52.7 degrees, okay? That's your velocity at that moment, okay? All right. Questions you guys might have on this? Yeah. So for this one, I think it's a little bit complicated because it's combination of the new concept of electric field with the what we learned in the previous semester, like the Newton's laws and then projectile motion, two-dimensional motion. So it's a combination of a lot of stuff here. Okay, so if you are not sure about some of these steps, you might want to go back and do a little bit of review. Okay, pretty much on the two-dimensional motions. That's for the most part of it. And then Newton's law will be giving you acceleration equal to force divided by mass. Okay, that's Newton's law there. Okay, but maybe a little bit review on vector and then also on two-dimensional motion there. Okay. All right. So if you don't have questions at this moment, we can probably move on to check on the last a few slides here. Um, the next section here talks about the electric field lines. Okay, so for like the problem we saw in the previous slide, we indicate the electric field by line. Okay, so basically, when we are solving a problem or if we want to visualize electric field, we use electric field lines. Okay, so these lines are not real lines, but they help us to visualize electric fields. Okay. So basically, we use electric field lines as a convenient way to visualize the electric field, okay? Three characters here. So for electric field line, they point in the direction of the field vector at every point, okay? So then you can know what's the direction of the field at any given point. They start at positive charges or infinity. They end at negative charges or infinity, okay? And they are more dense when the field is stronger, okay? So let me show you a couple of examples here, okay? So for example, electric field produced by a point charge, a positive point charge, okay? So you'll see that at any given point, you can see where the direction of the field will be, okay? So indicated by the arrow on the electric field lines, okay? And if this is a positive charge, so the field will point away from the charge, okay? So in that direction or in that direction, pointing away. Now, if this is a negative charge, so then electric field will point towards the negative charge, okay? The field produced by a negative charge will be towards the negative charge. On these two figures, you can see this is positive Q, this is minus 2Q. So if you represent in the same figure, you should also count the strength for the field. So because this is a 2Q, so you'll produce a stronger field at the same location away from the source, right? So you can see there's more lines here that indicating the electric field around this is stronger than the electric field around this charge, okay? Because you have minus 2Q here, you have 1Q there, okay? So electric field in this case start from the positive charge, but you point towards the infinity or end at the infinity. On this case here, it starts from infinity and end at the negative charge, okay? So these are two separate examples, but if you have the two charges are close to each other, okay, so for example, this guy here, if you have a negative charge and positive charge, they are close to each other, then this would be how the electric field lines look like. It starts at the positive charge and then end at the negative charge, okay? And then also in this case, now this goes to here and then curve up, coming back probably somewhere here, okay? So that's the scenario here. If you have a 2Q positive minus Q here, you'll see that you have more lines along the more charge point here, less lines around that, okay? So you can kind of count number of lines to identify the strength of the charges or the magnitude of the charges, okay? If you have two like charge, say positive and positive, so you'll see that it's electric field lines will start at a positive charge and then pointing towards or end at infinity, okay? The same case here. So then at the middle over here, you'll see that zero field because there's no line over here, okay? And we can see that because electric field by two charges at the middle will cancel out, okay? If they are like charges. All right. We can take a look at a couple conceptual questions here. Let me see what else do we need to cover. But maybe we can take a look at one or two examples here. Okay, so this one says the electric field lines surrounding the charges are shown in the figure down here. The center charge Q2 is minus 22.8 microcoulomb. What are the sign of Q1 and Q3? And find Q1 and Q3. All right. So for the middle one here, you can see nearby the middle one, you have more electric field lines. You will have 1, 2, 3, 4, 5, 6, 7, 8 on one side, and then the same on the other side. So totally you have 16 lines, right? Surrounding Q2. You have just 8 lines surrounding Q1, and then also 8 lines surrounding Q3. So number of lines indicate the magnitude of the or indicate the strength of the field, which is directly proportional to the magnitude of the charge. Okay, so you can see Q1 and Q2 are magnitude-wise, they are just half of Q2, or Q1 and Q3 are just half of Q2. Okay, but for the sign, what are the signs of Q1 and Q3? You can see the lines start at Q1 and then also Q3. So that tells you Q1 and Q3 should be positive charges because electric field lines start at positive charges, they end at negative charges. Okay, so from that you will see that Q1 and Q3 should be positive charges, and then they should be half of Q2 because they are having half number of lines surrounding them compared to Q2. Okay, so on this one, the answer for A would be the signs of Q1 and Q2 are positive, and then Q1 should be equal to Q2 equals to 1/2 of the 22.8, which is 11.4 microcoulombs. Okay. I can write it down here. So Q1 and Q3 are positive charges. B and C, Q1 should equal to Q3 and equal to 1/2 of Q2, which is 11.4 microcoulombs. Okay, for those two charges. Another kind of example here. So the electric field lines surrounding those three charges are shown in the figure. Again, it's asking you which of the charges are positive and which are negative, and then rank the charges in order of increase in magnitude. Okay. So remember, field lines start at positive charges. So that means QA is positive. And at negative charge, that means QB is negative. On Q3 here, the line starts out from Q3. So Q3 is positive. Okay. So QA positive, Q3 positive, Q2 negative. Okay. For magnitude wise, there's only 5 lines over here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 here. So this would be QA would be less than QB magnitude wise. You take absolute value. Okay, absolute value of QA should be less than QB, and then less than QC. QC has more lines than QB or QA. Okay, so A is less than B, less than C. Okay, in that case. All right. Then I think we'll stop here for today. Okay. So on Monday we'll have our exam 1. All right.